Morning. My name's Philip Collins, Victor Coot, Hotel 2 Whiskey Pub Charlie. I'd like to welcome you all to the 2019 CCARC lectures and to Dr. Brian Clarke, who's going to explain to us the meaning of, or the process of real science.
Thank you. Thank you. Okay. I assume you can all hear me well enough. No problems? Okay, good. Okay, it seems that I'm left with the job of pushing the button here, which is going to be fine, I hope. Oh, wait a minute. All right. Now, I'm going to assume that you can all read at something like 200 to 300 words per minute. I can only speak at about 120 words per minute when I'm going flat out. So I'm not going to speak from my slides. My slides are going to be coat hangers. And so I'm going to be addressing each of the headings there. But in some cases, there'll be slides with text on them. And I'll leave them there until I see your eyes glaze over or you fall asleep. And then I know you've read the slide. I have only 3 copies of the slides if people want to take notes for them. I don't know. I hand them around, see what happens. Now there is a paper that I've written that sits behind this, if you like, but it's about 15 pages. It's readily available, I'm told, on the Wyong Field Day URL. So the paper is available for you to read. I have copies here if you're stuck. Okay. Okay, now this is a little bit about me. I'm going to let you read that so that you can understand where I'm coming from. It doesn't say there that my first degree is electronics engineering and hence I'm a ham radio operator and all those kinds of things. I'm starting from when I started to do some actual research. Okay, everybody read that slide? Can I move on? Is anybody still stuck on that slide? Okay. Okay, so this is the area that we're probably in right now. This is the area that the ABC is in. So, around about 1950 or so, how many of you know of Ernest Hemingway? Old Man and the Sea, For Whom the Bell Tolls, all those good books. He was effectively a journalist when he first got involved in the Spanish Civil War at about the turn of the 19th century. And so a lot of his writing was from a journalistic point of view. He was then teaching journalism at New York University, and one of the people there asked him, what's the thing that a good journalist needs? And effectively he said, what every good journalist needs is a built-in, shock-proof shit detector. Now, people who've picked up his ideas since then have softened the word shit and called it crap. So I'm using the word crap detection for my talk. Now, most of this stuff here has to do with the person who's actually writing the material and the kinds of questions you can ask about where does this person come from, who's paying the piper, what happens if he falls over, all those sorts of questions. Those aren't necessarily all of the questions that are important for science, as you're about to see, but these are a good start in terms of the stuff that we're faced with every day. Oh dear, that's hard to read, isn't it? Okay, all right, okay, let's move on and see if the rest works properly. Okay. Now the first 4 of these are the things that a good scientist would be looking for. So correlation, temporality mechanism, all those kinds of things. The bottom three are the ones that journalists, Tim Flannery, Al Gore, those kinds of people will hop onto. And right at the bottom, it feels right, that's for the greenies, who like a really cosmetic, soft, sweet, wonderful life. Manipulability, good for politicians, because they like to be able to change the variables, particularly if they can tax it. Okay, now, how many of you have heard of Richard Feynman? Okay, we're talking to the celebrated few, I guess. Okay, Richard Feynman was professor of physics at Princeton University, effectively almost sort of shoehorned into the position by Albert Einstein, and followed Einstein through to become virtually the #1 professor of physics in the world. So the important thing that he comes up with is once you've done all of your hypothesis generation and you've gone and gathered data and you've tested your hypotheses, if it disagrees with nature, it's wrong. Now, in the 19th century, or in fact, late 18th century, John Stuart Mill, who was a sort of political philosopher, came up with what were now known as Mill's canons. And what he set out was a number of statements about how we know that certain variables are related to one another. That was his main thing, that he was concerned about the relationships between variables. So if you like, he was really on to correlation. Now, of course, when he was writing was before statistics actually had correlation coefficients. That came in the next century. Now, the example of eating rotten fruit. If you eat rotten fruit, and then every time you do that, you have to get to the toilet fairly quickly, then you know that you've upset your system. So you've got a good correlation between taking in rubbish and producing it. But catching a cold, if you're in a wet, cold situation, do you always just get a cold? Is there a correlation there? Or are we into some kind of etymological conundrum that somehow the housewives and housemasters have fastened on calling that nasty bit of, chucking up out of your nose and mouth a cold, and it has nothing to do with temperature whatsoever. We'll come to that a bit later. Carbon dioxide and temperature. Now, this is one that I'm going to delve into a little bit later on in quite some depth, because there are problems in how the data were gathered, and I'll come to some of those problems. Okay, this is the shape of the curve that Dr. Mann produced for the IPCC, the International Panel on Climate Change. And you see that it starts back at 1000 AD, comes through to 2000 AD. Now, the first curve that Robert Mann produced had a straight line along here and then took the average of these red bars. So he was showing his well-known hockey stick, all right? Now, for those of you who have read any history, you will know that between 1300 and 1500 was a mini ice age. Now, there was also a time when the River Thames was frozen over, part of the English Channel was frozen over, the agricultural stuff was frozen and couldn't be eaten. People died of hypothermia, and worse than that, because they couldn't afford glass in their houses, you had to be royalty to afford glass and shift your windows around, they had a fireplace in every room in the house. And where was all of that smoke going? It was going into the house and up into the chimney, and so the actual transmission of heat from the fireplace into the people was something like 5%. The rest was going up into the atmosphere, all right? And what was in that smoke? There was carbon dioxide, and sulfur dioxide, and phosphorus oxide, and nitrous oxides, all sorts of lovely stuff. But when you look at this curve, what happens between 13 and 1500? You've got this tiny little dip of 0.4 of a degree. That would almost freeze water if you stayed there for a year or so. But it wouldn't cause freezing over of the River Thames and freezing over of parts of the English Channel. There's another thing that you may or may not be aware of. There was a country a little bit further northeast of England called Greenland. Why was it called Greenland? Because it was green. And why was it green? It was because the Humboldt current that comes up from the Caribbean, I'll draw it your way, comes up from the Caribbean, goes across the Atlantic, and it was going around the west side of Ireland and straight up around Greenland and keeping it nice and arable. And that was when the River Thames froze over. There were problems between Ireland and Wales. All of that sea in there was pretty nasty, and the Thames and the English Channel were frozen. Then, of course, at some stage after 1500, the current changed. And suddenly we have warm water going up between Ireland and Wales, and we have warm water going in the English Channel, and the Thames is no longer frozen, and Greenland freezes over. So Greenland now has 1% arable land, where previously the whole land was green. Yet it doesn't appear. Now this is some later work. There are 7 different reporters' work in here. The black one is a fellow by the name of Briffa, who went through exactly the same data that Robert Mann had and has come up with a different set of curves that doesn't shoot off on an exponential at this end. All right, so one of the things that we like to see in terms of temporality is that the cause precedes the effect. Now, maybe that's something we're taught very early in our lives, and it's part of our sort of the etymology of the dictionary writers. They tell us that cause must come before effect. So maybe it's a brain problem that we believe cause comes before effect. But really, scientists like to see the cause coming before the effect. So when you're eating unripe or overripe fruit, and then you get the exhaust problems, in Latin that's post hoc ergo propter hoc, because of the event, or after the event, therefore because of the event. But catching a cold, now that's a bit different, because what's happening there is that you've been invaded by a virus. And it's a very gentle virus, the one that gives you a cold. But it's a constantly mutating virus, so that your system, your immune system, will gradually learn the signature of that particular virus. And you'll be able to last the rest of that period, maybe a year or so, without getting that particular cold again. But because it's a constantly mutating virus, next year your immune system doesn't recognise it, so you get a cold again. Now, carbon dioxide and temperature. Here we have a wee problem. When you were doing physics or chemistry at school, did you ever hold a test tube of water and put the top part of the tube over the Bunsen burner and have the water boiling at the top of the tube, but you were able to hold the bottom of the tube? You didn't get boiling water into your fingers. Anybody remember doing that? Ah, we've got one. Thank you. Right. Now, what's happening there is that the water is a very poor conductor. And that's what we're surrounded with. 70% of the Earth's surface is covered in water. Now, around the tropics, you have almost direct radiation from the sun coming straight down. And certainly between the tropics of Cancer and Capricorn, you've got virtually 0 degrees of incidence for most of the year. And so the water around the tropics is quite warm. Down where we are, 34 degrees south, of course the sun is glancing, our water doesn't get quite so hot, but as you move further towards Antarctica, then you're getting an awful lot of ice because the sun hardly reaches there at all. Maybe 3 or 4 months of the year. Now, if you bear in mind that there's that long time between heating the water at the top and the water at the bottom, then you've got the beginnings of a mechanism. Now, where does carbon dioxide come from? The bulk of it, 85% of the carbon dioxide that we have in our atmosphere comes from volcanoes. And the bulk of them are under the oceans. And those volcanoes produce carbon dioxide, which then, because of the lower temperature at the bottom of the ocean and the higher pressure, goes straight into solution. And then, because of the way in which the Earth is rotating, centrifugal force carries that colder, lower water up towards the tropics. But it takes quite a while. It's probably only doing 30 or 40 K. So it's got to travel several thousand K to get to the tropics. And of course, the water up there is warmer, and so the carbon dioxide comes to the top and gets exuded as a gas. What's the other thing that we know about the tropics? It's very green. And how does it become green? Because it takes in that carbon dioxide and through photosynthesis turns it into food, plant material of course, fibre, and what we love most, oxygen. Okay? So that if we decide that we're going to act as a government and we're going to allow people to clear vast forests in order to allow for the developers to put up new buildings and to plant all of that grass in concrete, we've got rid of all of that green area, which is going to take in the carbon dioxide that we produce and turn it into oxygen. Now, if we know that there's quite a time between the volcanoes producing the carbon dioxide and it travelling up towards the equator, we have a time delay. Now, that time delay between that carbon dioxide and temperature rise is between 200 and 1,000 years. Now, if you remember those two curves that I put up earlier, the Dr. Manns and the Briffers, and you take the temperature curve and you move it around until it maps across the carbon dioxide one, you'll find you can get the two signatures to map. And the gap, on average, is about 800 years. The range, 200 to 1,000. The problem is, it's the other way around. The temperature rises, then the carbon dioxide percentage in the atmosphere rises. So it's exactly the opposite of Mann's hypothesis. Okay, we've been through influenza. Aristotle, 366 BC, started observing that there were fossils of plants around and the plants no longer existed. And so he started coming up with the beginnings of our present-day notions of evolution. Now, I don't know whether you can all see this picture that I've drawn over here. Everyone see that all right? Okay, so and I'll turn it a bit. So this fellow here is El Sol, 93 million miles or however many kilometres away. And here's the grassland underneath. And this thing is turning out a very broad range of waves, sort of infrared through to ultraviolet, including the small range that we can actually see. But I've coloured this red because it's the infrared rays that I'm really interested in. So if the infrared rays are coming directly down to the surface of the Earth is a fairly good absorber of infrared energy and starts warming up. Clouds, on the other hand, are mostly ice. That's why when you see clouds forming, they look white. And that's because the ice crystals are on the outside. When the clouds are grey, that's because they're sufficiently thick that the sun can't get through all of the ice. So if the rays going through to the clouds, they'll be attenuated. They aren't going to cause so much heating down at the surface of the Earth. Now, let's say during the day you have no clouds and you're inundated with infrared. The temperature on the surface of the Earth, where there are no clouds, will rise. Where there are clouds, the temperature over here will not rise so much. Now, okay, so let's assume that we've now moved from daytime into nighttime and you've got a large cloud cover. Then the Earth, trying to radiate out into space. Out here it's minus 273 degrees centigrade. The heat's not going to get through the clouds. And so the Earth is going to stay relatively constant, relatively temperate. So those are, if you like, some of the laws of physics about how temperature and the infrared coming in works. But it's a local effect. It's not a global effect. Okay, we do have the sun. When the energy arrives at the surface of the Earth, it's about 1 kilowatt per metre squared when it doesn't have these fellas in the way. But when these fellas get in the way, it can be down to 0. Okay, we've covered where the carbon dioxide comes from. Now, is carbon dioxide the really bad apple? Okay. What I've done here is I've looked at the various gases that are alleged to cause us problems in terms of a wet blanket effect on the Earth. And so here we have water at the top, or if you like, steam, as in our clouds, carbon dioxide, methane, nitrous oxide. They're the main ones. The rest of the gases in the atmosphere, oxygen and nitrogen, about 97% of the total atmosphere, is relatively transparent through infrared. So here we have percentage by volume, and then the specific infrared absorption effect compared with carbon dioxide. All right, so water is about 10 to 20 times more effective at absorbing the infrared than carbon dioxide. If we now weight that, so we're multiplying these two columns together, we get this column here. And then if I zero all of that and call this 1, I get this column giving you the weighted absorption effect normalized to carbon dioxide. Now what you can see here is that it's actually the water vapor in the atmosphere that's going to cause most of our temperature changes at the surface of the Earth. So how do we control that? Well, human beings are about 60% water. So one of the ways we can get rid of water is to kill human beings. Probably not acceptable politically. Another way of getting around these problems is to kill rainforests. So that'll then stop the carbon dioxide. But that's expensive compared with changing the water content. But how do we change the water content? We can't. We don't really know how to. We don't have the mechanisms. And most of the water content that we're getting is from winds picking up water off the surface of the oceans and blowing them across our continent. And we don't have the energy to do that. So all of this stuff that the governments are doing of saying, oh, we're going to go for the Kyoto principle or the Paris principles and so on, and we're going to do 2% reduction of carbon dioxide. What effect's it going to have compared with the water effect in our atmosphere? SFA. Now, I'll just race on. Okay, iceberg melt and sea rising. This is a picture that the ABC loves to put up time and time again whenever climate change becomes on the horizon again as an important political topic that the ABC has got to produce something about. And they use almost exactly the same picture every time. This is the Totten Glacier in Antarctica, and it's taken from a helicopter going almost straight in. So you can see that there's actually a rise in the surface here. What causes the glaciers to calve? Okay. That's part of it, but the other part is that the ice is sitting on top of earth and rocks that have been rumbled and rumbled and rumbled, which then become rounded and smooth. They become the moraine. And that moraine acts as a sort of low friction device for allowing the glaciers to move towards the edge of the land. But it takes about 1,000 years for that effect to occur. But the ABC loves putting this up and claiming that somehow this is related to climate change. Now, the ice and the water here, well, the ice doesn't absorb much water. This absorbs a little bit more, but unless there's a huge wind blowing the water into the base and eroding the base, heating up the water near an iceberg isn't going to cause calving. Bit of a problem. Okay, I've mentioned the Gulf Stream and the Humboldt Current. Okay, ice shelf calving. If the landmass was totally flat and the ice built up uniformly, then you might have difficulties predicting what would happen when the ice melted. Now, there was a fellow who did some work on this and said, look, if all of the ice on Greenland melts, and he claimed that the thickness of the ice was about 3 kilometres. Now, I've got no reason to doubt that, but if all of that, if all of the area of Greenland was flat, and if the top of the ice melt was flat, and that was 3 kilometres above the landmass, and it melted, then the average rise in water around the Earth would be about 6.7 metres. But what flat landmass around the world do you know of that is totally flat? None that I know of. Everywhere you look, except around the coast where we have volcanic effects.
Yeah, but that's only a small portion of it.
Sure. Okay, also you might say the Gobi Desert, and you might say parts of Sahara and parts of Egypt are relatively flat, but they're away from water. So we're talking here about the effect of ice melt. We don't have ice very much in this country, so we're not worried about that. Now, there's a wee problem here with ice and melting. In 1066, when the French came over and persuaded us that we should speak French and that we should really lick the French bottoms, and they invaded our language and they invaded our land, and they built rocky castles all around the place and so on. The main fighting was at a place called Senlac Hill. Now, Senlac Hill was at that time at sea level, which made it possible for the Normans to get in and beat the shit out of the Brits. Nowadays, it's 30 metres above sea level. How did that happen? This is 1066, remember? The last volcanic activity in Britain was 946 AD, 120 years previously. So you can't say that Senlac Hill was pushed up by volcanic action. But my question is, what happened to the water? What happened to the 30 metres of water? Where did that go? Where'd it go? Very good. Yes. Evaporated and formed clouds, which then insulates the Earth. That's very good. Now, one of the things that the people who talk about the melting of the ice on Greenland forget about is that once the water melts, the laws of physics with respect to vapour pressure do not suddenly disappear and become zero. You're going to get clouds over Greenland, which is going to slow down whatever is happening, the warming up of Greenland. So you're going to get a sort of a recurrent spiral of water melting, or the ice melting, turning into vapour, forming clouds, and slowing down the melting. Now, the other assumption behind the 6.7 metre water level rise is that the Earth is spherical. Is it? No, it's an oblate spheroid. Yeah. The other thing is the gravitational force at the surface of the Earth equal everywhere? No. So why do we not have the 6.7 metre rise everywhere? Because the water is subject to gravity, and so it's going to go in places where the gravity is higher. It's also going to accumulate around the equator because of the m omega squared r effect, centrifugal force. Now, is temperature rise all that bad? In the, late 18th, beginning of the 19th century, when temperatures were much higher than they are nowadays, There was a huge amount of science going on. There was a huge amount of exploration. This country was found. Cook was doing his sailing around, 1769. Frobisher was around. Drake was around. Magellan was around. A huge amount of exploration and discovery of new lands. Technology. We had Voltaire, Ampere, Henry, all of these people that we know, whose names have now been given to us for our electronics materials. And so when the temperature rises, we seem to get more intellectual property being developed. People can sit and think. They don't have to worry about wrapping themselves up and getting away from the refrigerator that's out there in the atmosphere. Should we cut fossil fuel use? All right. Now, the first automotive vehicles that were mass-produced were probably the Stanley steamer. And some of the greenies would love us to go back to the Stanley steamer. And the reason they say that is the only exhaust from the Stanley steamer is steam, which is then going to form clouds and then it's going to fall as rain, so we've got a nice little cycle of the water going back and forth. What heats the water to produce the steam? In the early days, yes, it was coal. And so it produced a lot of the normal stuff that we have nowadays, all the carbon dioxide and so on in the air. Okay, then along came Monsieur Carnot, who produced for us the first the IC engine, internal combustion engine. All right, and it was designed at that stage to run on any kind of fuel that could be vaporized and then could be ignited with incoming oxygen from the air. Now, in the early days, of course, the fuel was pretty rubbishy. It was pretty close to butter and grease, and so it had to be heated up. And the compression ratio would have been sort of 3 or 4 to 1. So the actual efficiency of the engine was probably 1 or 2%. Now, very much later in the development of the internal combustion engine, we have Joe Lyons producing the hemispherical head on the Jaguar engine. And that's getting up to sort of 15 to 20%, depending on how well you tune the engine. And then you have the people in California saying, oh, your engine's turning out too much carbon monoxide. So Jaguar hired a fellow by the name of Brian Mays, who designed a new head for the Jaguar engines, the squish head, and immediately got down from 1 to 2% carbon monoxide to 0.2% in one hit. So no need for catalytic converters in the exhaust systems, just by redesigning the combustion chamber. And he got the efficiency of the engine up to about 25%. Now, unfortunately, most of us can't afford Jaguars these days, so just take my word for it, but it's a very efficient motor vehicle. I've owned 4 of them, so unfortunately my wife drives it. She gets very low miles per gallon, whereas I can get quite high miles per gallon. Then we have Herr Dr. Diesel coming along with another kind of internal combustion engine, but using a diesel fuel and relying on compression to perform the ignition. Now, with petrol engines, we can only run at about 8 to 1 maximum with the stuff that comes out of our petrol pumps. If we use LPG, it has a lower octane rating, and so you can't use it at the 8 to 1 compression ratio. You actually have to put in another head gasket, or you have to retard the spark so you don't blow the engine apart. With the diesel engine, you can run at 16 to 1 compression ratio, and you can get something like 40% conversion of the energy in the fuel onto the road. So if you like, oil well to wheel type of efficiency going up to 40%. Where's the other 60% going? Heating of the engine, heating of the air, burning of other fossil fuels, producing carbon dioxide. And what's really lovely about diesel engines is that it produces little particles that the petrol engines don't. And these little particles lodge in our lungs and give us problems called asthma. Now, that's not such a bad problem if you've got a diesel engine truck and you keep taking it in to be maintained so that the injectors are always clean and the combustion is set up properly so that you have very low particulate matter. But if you decide that you're going to have your main warehouse down south of Appin or Camden or whatever, and then you're going to use trucks to feed all of the shops all around the place, your cheapest way is going to be by diesel vehicles, and you're going to run them all day long. So if you go along Victoria Road in North Ryde, there are diesel trucks almost all the time, all right? Now, where there's this high concentration of diesel vehicles, oops, we've lost something there. I don't know whether I can wake this up again. Oh, don't do that to me. Okay, right, we're back again. Good. Oops, too far. Okay. Oil-fueled engines, how are we going to do? Okay. So there's this high correlation between asthma and diesel motor vehicles on the roads outside our houses. Now, as good scientists, we should ask, is the asthma causing the diesel trucks to run on the road? Probably not. Are the diesel trucks causing the asthma? We don't really know, except that when you examine the lungs of the people at post-mortem, you find they've got a lot of particulate matter in there. So there's some kind of connection there. Now, I might say that there's maybe a third variable, that when you have noisy trucks going up and down the road, you know when there's a diesel truck outside because of the compression ratio. The engine is not insulated normally. And so while people are sitting in the cab driving and they're well insulated, they can't hear the engine. But you outside, you hear this continuous, very high metallic noise coming out of the engine. And if that's going on day after day, up and down the road outside your house, the chances are you will move away. And so that then means that the low-rent people move in, and the low-rent people probably have a very poor diet, which may mean that they don't learn how to deal with asthma and other kinds of lung problems. Just a hypothesis. All I'm suggesting is that we don't really know the answer there, although there is a strong correlation between diesel trucks and asthma. Should we go to electric vehicles instead? Now, wouldn't that get rid of the whole problem? Or would it? What happens with electric vehicles? Okay, there's two different kinds of electric vehicles. There's the pure electric vehicle, where you have batteries in the vehicle and they drive an electric motor. And if it's a very cheap form of electric vehicle, it'll have one motor, differential, and it'll drive one set of wheels. If you have a slightly smarter vehicle, it'll have a wheel motor in each and every wheel, and there'll be a central computer which senses how much current to provide to each wheel depending on where you are in terms of skidding sideways or accelerating too fast and causing some wheels to lose traction and so on. And so it'll adjust the amount of traction at each wheel. All right, that's one form. That's the pure electric vehicle. The other form of electric vehicle, which seems to be catching on here, is where you have that same kind of electric motor, and it may be electric motors in each wheel, but you have on board a small internal combustion engine to actually charge up the batteries. And with those vehicles, you're getting something like, in old money, 1, 2, 3, 4, whatever it is, litres per 100k, compared with the average car, which is somewhere between 7 and 12 litres per 100k. So it looks very efficient. But the vehicle has now become so complex, electronically and mechanically, that you and I couldn't get in there to do any maintenance work. And so it's a real bonanza for the mechanics. Whenever there's a problem with your vehicle, you've got to take it to the mechanic, and you've got to go along with your bank manager or your checkbook and make sure that it's got 3 zeros on the end, and all that sort of thing. Now there's worse to come. Say we have our pure electric vehicles and we're going to charge them up overnight. There was a fellow by the name of Limbruggen, a mechanical engineer, who actually built an electric vehicle, built a bus. And he used it for shifting people around, and he thought, this is the way to go, that we should all have electric vehicles. And his view was that the batteries could be charged overnight. And his hypothesis was that all the generating capacity around Australia was idling overnight. Really? Where did he get that idea? I don't think he ever visited any electric power station. But anyway, if I look at the total amount of fuel that's consumed for internal combustion engines, and I then compare that with the electrical energy required, we'd require something like 7.6 times the present capacity of the whole electric grid in Australia to power our electric vehicles. That's quite apart from driving your air conditioning, your toaster, your refrigerator, your air conditioning and all that kind of thing. So we need 8.6 times the total capacity. So we've got something like 46 gigawatts capacity. We'd have to go to, whatever that is, you can multiply that by 8 yourself, 400 gigawatts. And because we've decided that we're not going to go to nuclear power, where's that power going to come from? Okay, the softies will say, okay, we'll have solar panels on everybody's roofs. Now, I've worked out that if you could persuade everybody in New South Wales to cover all of the north-facing roofs of their houses with solar panels, you could just about do it if you had 9 hours of sunshine every day. Will that happen? Unlikely. But that's the sort of area that you need to cover with solar PV panels in order to provide the energy to run electric vehicles. So electric vehicles aren't going to solve the carbon dioxide problem because you'll put in more and more generators that run off fossil fuel. So you're going to produce even more carbon dioxide. Isn't that wonderful? No. Okay, you've seen that picture. Now, here we have, I've just been talking about this. Here is the blue lines up here is the total gigawatt capacity of the Australian generating system. And this red line here is a prediction of demand. The green line is where the data stopped in the Australian Bureau of Statistics. And so you can see we've got about 15 gigawatts of spare space, apart from living in South Australia, of course, where they're beholden to Elon Musk and his millions of 18650 lithium cells. Okay, how can we solve these problems? Well, I think that one of the first places that we need to start looking is in terms of educating our politicians and educating the editors who run our media, to actually teach them about causality and those 4 requirements of having correlation, temporality, mechanism, and null-tested hypotheses. Now, all we're getting at the moment is correlation. You know, Michael Moseley's "Trust me, I'm a doctor." Yeah, right. And Tim Flannery sort of flanneling away about how wonderful he is. And of course, we have all of our wonderful weathermen who say, it's the hottest we've ever recorded. I say, yeah. When did you start recording? Now, when did we start recording anything, ever? It was only about 5,000 years ago. Do we have records going back 5,000 years for temperature? No. So what do the scientists do? They'll go down to Antarctica and they'll drill bores down into the ice and they'll pull it up and say, here we have data for 160,000 years. But carbon dioxide vaporizes at minus 78.5 degrees centigrade. So are they measuring carbon dioxide in those ice cores? No. Because they're doing all this work in room temperature. And so they do things, they say they're looking for proxies, things that occurred at the same time. So they're looking for regelation interfaces in the ice cores. Regelation is related to temperature. So they're saying, here we have a temperature-related thing related to temperature. Yeah, wow, I'm really impressed. Not. They haven't actually got the data. That's the problem. And then the last one is what's 2%? That's the reduction target that we're going for, 2% reduction in man-made carbon dioxide. 40% of the carbon dioxide comes from our power stations around Australia. 0.03% is the proportion of carbon dioxide in the air. 3% is what we can do about it. And when you multiply all of that out, you get something like 10 to the minus 8. which is about as good as homeopathy. You know, the business of an eyedropper in a swimming pool, that's about 10 to the minus 8. Okay, all right. Your time for tearing me apart. Yes?
What's the reasoning and effect behind neurometeorology doing homogenisation of temperature records? That's hit the news just recently and
Okay.
done a couple of years ago as well.
Okay. When Robert Mann first started producing the IPCC data, he was using temperatures that were recorded at places where they are customarily recorded. So that would have been around the coastline of Australia and around conurbations in other built-up areas and around airports where the weather is important. And so measuring of temperature over the water, measuring temperature over deserts just wasn't there. So what they're now doing, now that we have SPY in the sky, they're taking readings of the temperature of deserts and so on and multiplying by the land mass and then averaging it for the population density in those areas to see what the effect is. And that's the data you're now seeing. So it's been adjusted. But do they measure temperature and carbon dioxide concentrations in the same place? Not that I know of. Any other? Have I bamboozled you all? Oh my golly.
You said that the ice cores had no carbon dioxide in them, basically.
No, they did probably have, but by the time they get them out and lay them out in their metal trays, at room temperature, the carbon dioxide will have flashed off.
Isn't the carbon dioxide in bubbles within the ice? And surely they know that it's within bubbles in the ice and don't just leave it out to flash off?
Maybe the bottom part, you know, it's 160,000 years old, will be sufficiently solid that the gas cannot get through. But ice, if you've ever examined ice under a scanning electron microscope, you realise it's not solid. It's full of little fissures, so the gas escapes very quickly. Yes?
I don't agree with that. I did ice core drilling inland in Casey in 1974.
Right.
And the cores that we pulled up, the gas trapped in the ice is under considerable pressure.
Yes?
You can get a piece of it and put it into a drink, and you can
And it'll
hear
fizz it away. Yeah.
Yeah, you can hear the. So that gas is trapped in the ice, and it explodes when it gets near the surface.
What I'm getting at is that measure of carbon dioxide in Vostok in Antarctica is not in the same place as we're measuring temperature on the surface of the Earth. All right, so you can't say that because there was carbon dioxide measured down in Antarctica that this was the same carbon dioxide concentration that we had in the rest of the world.
Okay, how much difference is there in the concentration of carbon dioxide around the world?
Nobody's actually measured that. All we have is Mann's work where he's taken a set of data and publicised it.
Given the amount of air movement, surely there's a fair amount of mixing of gases within the atmosphere.
To a certain extent, but we also have cloud formation which changes the concentration of gases because some move more quickly. You know, the heavier molecules are going to be slower than the lighter molecules. So, you know, Halleberg can often example. Yeah, okay. So carbon dioxide is one of the lighter ones, and it's going to move very quickly, whereas nitrous oxide and so on are going to be a bit heavier. Phosphorus oxide is going to be really heavy, and it'll be much slower getting out.
Okay, well, given the carbon dioxide is one of the lighter ones, surely it mixes better.
Sorry, it's Julius.
So given that you just said carbon dioxide is one of the lighter ones,
Yes.
does that imply that it mixes more readily?
No, it probably moves more readily.
Okay, so therefore the distribution would be more consistent than some of the heavier molecules you just mentioned.
That's an interesting hypothesis that has yet to be tested. See, unfortunately, most of the people who are hopping onto Mann's hypothesis of that sort of exponential rise of carbon dioxide and temperature at the same time, and ironing out the many ice ages between the 13th and 15th centuries, are relying almost entirely on Mann's statistical methods. And subsequent researchers have not found the same kind of exponential rise in temperature. So What you find is the ABC still thinks man is the greatest thing since sliced bread. But they don't talk about Briffa or any of the other people who've said, no, statistical artefact.
The temperatures are actually rising.
Up until 1998.
Still.
Well, some...
Have a look at the NOAA figures on the NOAA website.
Yeah, but if you try to measure an average temperature of the whole of the Earth, you'll find that it turned over in 98. Okay, maybe in Australia right now we're having temperature rises that seem to be very much higher than before. But if you take it over the whole of the Earth, we also have places that are much colder. Like what's been happening in the Northern Hemisphere right at the moment. They're having ice storms that they've never seen.
That's temperature, not climate.
Sorry, that's temperature?
That's temperature, not climate.
I understand that, but yes, but unfortunately most of the reporters are meteorologists. And the meteorologists are concerned with predicting something that's going to happen in the next 1.3 seconds. They're not concerned with going about 100,000 years before, or 200,000, or 20 million, or 60 million to the beginning of hominid life on Earth. We don't have that data.
No.
But we do know that people have survived in the Sahara and people have survived in Siberia. Very much bigger temperature ranges. And even here in Australia overnight, we can get 5, 10, 15 degree temperature changes. And we adjust. We change our clothing. Or we change the insulation that we have on our beds. Or if we go to work, we have air conditioning and we just dial up 21 degrees. And if we're really adventurous, we travel by train. And in the cold weather, everybody's sneezing away. And of course, earlier in the day, the air conditioning system is recirculating in there to save energy. And so you're getting everybody's cold put straight into your alveoli, making it absolutely certain you're going to go away with a cold. Isn't that wonderful?
Any other questions? I'd be happy if they could tell me what the track would be like on Tuesday. Thank you very much, Brian.
Thank you, thank you, thank you, thank you. I'll let you...
Presentation.
Oh, my golly.
Yeah.
Thank you, thank you, thank you.